stands for? Alright, Mavericks table, what does K stand for?
Just like, what does it mean if I say, okay, the variable K, it stands for the what?
No, that you're thinking Kelvin. CJ's table, what does K stand for? What's the whole theme of the day? The whole theme. The second part of the web quest. Okay, what did you guys say? Equilibrium. Okay, so K stands for the equilibrium. Anybody? Constant. Woo! Okay. Step 1, equilibrium constant. And K gives us a lot of information about a reaction at equilibrium. So we had two versions of K, really three, but K greater than 1 and K less than 1. Discuss that at your table. What does the K greater than 1 mean versus what does the K less than 1 mean? I'm getting you to pull out a little bit of knowledge from your background. All right, Camilla's table. Tell me what you guys think. Greater than 1, less than 1. Give me one of them. Your table. Okay, so there's something about like a difference in numbers, which are indicating higher or lower amounts. Wesley's table? Okay, so guys, we're talking about reactions, right? There's some very constant things. We always talk about reactions. What and what? Products and reactants. Reactants and products, right? Okay, so the K is the equilibrium constant. It's a value. It's a value that's either greater than 1 or less than 1, okay? And that value is going to give us an indication of reactants versus products. Linear table. Pick up from there. They mentioned higher and lower quantities. I'm trying to get you guys to reference the nature of reactants and products. What do you guys think K greater than 1 represents?
That the reactants are...
You're on the right track. The reactants are
higher.
Okay, one of them is higher. Okay, so what we have to know is how is K set up. So we had an expression where you wrote out like the way you would quantify K, the way you would calculate K. You guys remember what that was? It was something over something. I'm trying to get your memory a little bit intact. I am going to review this, but let's see. Whatever what. You had a reaction. It was like A plus B equilibrates to C plus D, where these little letters are coefficients. What'd you guys say? It is simply products. It's the concentration of the products. Brackets mean what? Concentration in what concentration value? Molarity, okay? Products over reactants. Okay, you are math savvy people, okay? If I have a value that's larger than 1, is the numerator or the denominator a larger number? Duh, right? Like we know that. That number has to be larger than this number for this number as a whole to be greater than 1. So, if K is greater than 1, who do I have more of? Numerator or denominator? Products. I have products. I'm going to call that being favored. This is the term we use just to indicate that they're in higher quantity. Okay, so take a stab at what K less than 1 is. Okay, that means that you have more reactants. So reactants are favored. Does this ring a bell at all? Okay, we know that it's got to be set up this way. We are going to get into the nitty-gritty specifics of this with some examples, but in general, we at least should pull from that. There's graphs that we can use to represent this. There's this little expression we can use to represent this. There's the value itself that we can use to represent this. Basically, all of this is just telling us in a reaction, who do we have more of at equilibrium? Do we have more reactants or do we have more products? And then what does that matter? So we know what can we do with that? Okay, so are there any units associated with K? Yay or nay? nay, okay? So because we have a ratio of molarity over molarity, we tend to just say all the concentrations cancel out, therefore there are no units represented in the end, okay? So what we should know is I'm going to have you definitely write down some of this, but some of this is going to be just pulling from a review from your actives you did Friday, which thank you. I did get most of yours, and the sub left a really good note, so appreciate you. Okay, so what we've been dealing with our entire chemistry lives is that reactions get to completion. Reactants A and B react, they yield, so we've always had a single arrow, they yield products C and D, and we were just like, hey, yep, that's it, limiting reagents and stuff can occur, but all reactants react, is what we always assume. And we had all these different characteristics of reactions, which were like giving us indications chemical changes were occurring. Gas evolution, forming pure liquids like water in a neutralization process, forming a precipitate. We had all these great images or illustrations of chemical changes that would give us indication 100% completion. Well, what we now are aware of is that that's a little bit of a lie. We have reactions that can go back and forth, back and forth, back and forth. So what's that word that means constantly changing back and forth? Dynamic, right? So we have reactions that are going to, now we're going to recognize that reach dynamic equilibrium. And again, dynamic means what? Constantly changing. And all that means to me is that reactants yield to form products, products form reactants, and back and forth, back and forth. But at some point in time, we have to call it equilibrium. We have to say that this reaction is at equilibrium. And there's a definition for that. Can you remember it? I can get you started and say the rate of the forward equals to the rate of reverse. That is the definition of equilibrium. Okay, so right here in red, equilibrium, the rate of the forward reaction, which is reactants yielding products, equals the rate at which the reverse or the backwards reaction is occurring, which is where products go back to reform reactants. That's your literal definition. So it is at that point, and these little arrows always get shifted around, guys, sorry. It is at that point we start to use these little double-headed arrows, or two arrows like that. And what you should know, now we're sit down, take notes with us, what everyone with the rails is. And what we should know is as these reactants are reacting and products are reacting, we're kind of going back and forth, back and forth, back and forth, we're never consuming all of any of them. We always have reactants and products remaining, always. There's at least some of both sides, reactants and products. But despite them constantly changing, there's no net change. Okay, despite that constant change. So I could give Maverick $20, he gives me $20 back, I give him $20, he gives me $20 back, I give him $100, he gives me $100 back, I give him $5, he gives me $5 back. What happened? Nothing. We just exchanged some money back and forth, that literally no change occurred. So one thing to note is despite the fact that we're at equilibrium, everybody thinks, oh, equilibrium means equal. It does not mean anything is equal except for the what? The rate, okay? So be very clear. It does not mean that product concentration equals reactant concentration. What does this little bracket mean again? What unit? Molarity. Okay, so that's a big misconception. Do not think that. So maybe if you need to write that out as like this is incorrect or a misconception, that might be helpful to you. And then occasionally to indicate this whole K value thing, being greater than 1, less than 1, they're the arrows that kind of get skewed. And so if you see the arrow pointing in a larger vector towards the products, what do you think that kind of means? It means K is what? Greater than 1. It's trying to tell you that the products are being favored by pushing them that way, and then vice versa. K is less than 1. So that's just another way to write the arrows, but you won't see it terribly often. I just wanted to let you know that before we move on. All right, so definition is what? Rates are equal. Okay, what's left at equilibrium? some of everything, some reactants and some products. Basically, we don't wipe out one side or the other. And is there a net change? No. Okay. All right, so the definition of K, which is the equilibrium constant, is it's supposed to represent the extent to which the forward reaction is occurring. So K is the extent of which the forward reaction is occurring, but we always have to have experimental data to give us that kind of assessment. So I'm going to let you read this and write down what you need to, because we've discussed a little bit already. We're going to do a little sketch of what a product versus reactant situation would look like over the course of a reaction. So since we're still dealing kind of with rates, which were rates what we talked about before we did the iodine clock reaction where everything turned black, we had a graph that we had to use. Do you remember what these axes were? This over here, y-axis was what? What do we measure with rates? Amount, but what was the amount unit we decided to use? Molarity. Oh, who said that? So thank you. So this is concentration versus time, because rate is always versus time. So over the course of a reaction, if the K value is showing the products being favored, who do you have to have more of at equilibrium? If over time, the K value, which is when equilibrium is achieved, the products are favored. What does it mean when they're favored? There's more of them, okay? So at equilibrium, who should I have more of? Products. Not a trick question. This is just trying to get you to see what that means, right? So that means I'm going to have a higher concentration of products than reactants, so I'm going to have those lines appropriate. So all I need to do is draw. What we drew before, where let's put the reactants in this green color. Okay, so you guys draw this as well, reactants. And I'm going to show them starting high, and over the course of the reaction, what's probably going to happen to reactants over time? They're going to react, and they're going to what? They're going to decrease. They're going to get used up. So I'm going to draw them kind of sloping down, and then the slope kind of steadily flattens out. And then they're going to flatten out, flatten out, flatten out, flatten out, flatten out. Okay. What's going to happen if we start with all reactants and the products start down here? What's going to happen to those products as the reactants get reacted? Right? They do what? They increase, right? Law of conservation of matter. As reactants react, products are formed. As reactants go down, products go up. So I'm going to draw those increasing. And then I've got them crossing lines. It doesn't matter if we actually crossed or not, but in this case I had to because this is how I drew my graph. But as the reactants start to level out, the products also level out. So your job is to decide, okay, when was equilibrium achieved? So I'm going to point, my laser's not hooked up right now, so I'm going to point. Where has equilibrium been achieved? Just tell me now whenever I get there. So when I cross, that's when the concentrations are what? Equal. Is that what equilibrium stands for? Okay, keep going. Now-ish, I'd say, okay, is this slope changing? It's it's not perfect. I was hand-drawn with a marker board, okay? So this is not changing slope, and this is kind of not changing slope. So what it's trying to show you is that despite the reactants are still reacting and the products are still being produced, there's no net change. So I would say about time here-ish is when equilibrium, it's here, equilibrium is achieved. I before E, except after C? That only works like occasionally. Is that right? Also doesn't look right, but we're just going to keep moving. Okay, so at the point where the slopes are the same, that means the rates are constant. And who did I show at the top? Who did I show in higher concentration? products, which should be indicating K is greater than 1. So it should products being greater. All right, you draw the same thing, but draw for K less than 1. Draw a very similar graph, but with K less than 1, meaning what? The reactants are favored, meaning the reactants are in higher quantity. All right, use 2 fingers and draw those lines for me in the air so I can see what's happening. All right, so did you guys start with reactants up high? Did you? You didn't have to, but I figured you'd start off similar. But so reactants and products level out, right? No crossing of the line here, because if that crossed the line, who's going to be on top? Products, right? So I'm just going to draw this one kind of going down with not an increased slope there at the end. And this one kind of going up like that. And then where is equilibrium achieved? About at the T, so kind of where the slopes are going to be constant. Looks good. Okay, so now you guys can tell that though there's changes occurring, a graph can indicate to us that the constant nature of the reactant concentration and product concentration means that equilibrium has been achieved. Now we know what K represents at least. We're going to learn how to calculate it now, but we know what it represents, and then we know how to look at it graphically. So far, so good. Okay, so here's that faux equation that walks through just a generic setup for K. What you have to do is you have to use the coefficients as exponents. Good. So we still are going to stack it as products of reactants, but we have to use the exponents this time. So what we're going to do is say K is equal to concentration of, who's the first product, Riley? First product. C raised to the little c power, where that's the little c. Manov next. So we're going to multiply that by the concentration of product D. So check, we've used both products. Raised to the lowercase d power, because that's whatever the coefficient of that is. SD's over what? Okay, so concentration of A raised to the lowercase a power, Kendall, times the concentration of reactant B raised to the little b power. Okay, so we have that general setup that we'll use every single time. The big point though, make sure you know this, I don't have any states of matter indicated on this reaction, so there's no qualification on this particular generic equation, but you will never ever ever use any pure solids, which how will you know if something's a pure solid in a reaction? How will you know? Say again? Bryce? Well, like I could have just fluorine, like diatomic fluorine. Guys, how would I tell you something's a solid? By the little s. Woo. Okay, I would literally put a little s next to it to say, this is a solid, don't use it in the expression. Whereas this is the expression, of course. How would I know if something's a pure liquid? A little L. Okay, I'm not making secrets here. I'm not trying to make it a mystery. It's going to be blatantly obvious if it's a solid or liquid. Okay, so I've shown you a concentration setup where it's like concentration times concentration over concentration times concentration. We call that Kc sometimes, where the C represents, guess what? Concentration. So sometimes it'll say, find the Kc. Don't think it's anything different. It's just the way we denote it sometimes. So in the end, you should realize that we're still talking products of reactants. So what does this actually mean? It's just the relative amounts of reactants and products, or aka the ratio of reactants and products at equilibrium. Give me a thumbs up when you're good. So I am going to show you Kp next. Does anybody have any idea what the P would stand for? Because we're going to talk about products and reactants all the time. So we measure things with concentrations. That's one way of measuring things. What's another way we can measure things? That starts with P. Pressure. It's actually pressure. Okay. So this one, I just want you to write down this right here as a setup because it's no different in terms of what you're plugging in. It just looks a little different. This one looks a hair different. So the first thing you hook in here says K what? KP. And then instead of putting brackets, because we're not using brackets, because brackets mean what? Concentration. We're putting P as in partial pressure of C raised to the what? Little c power, the coefficient of whatever's in front of C. This is assuming the same equation we had on the previous slide. D raised to the little d power, A raised to the little a, and B raised to the little b power. Again, we are using coefficients. There's only just a P there to indicate pressure instead of concentration. SD, you with me? Okay. Thank you. All right, so let's read out the equation for the formation of ammonia from its elements. Write that at your table. Formation of ammonia from its elements. If you don't remember what ammonia is, anybody? NH3. NH4 is ammonium cation. So formation of ammonia. NH3 is ammonia. All right, Wesley's table. What's ammonia? The formation of ammonia from its elements. Huh? No, formation of ammonia. N2 as in nitrogen gas, yield or plus 3. One more time. H what? Okay, so H2. You're good. I was just making sure you said 2. And 2 ammonia. Good. Okay, so you guys balanced it. Appreciate it. Okay, so we have ammonia formed from its elements. Most of the time, nitrogen is a gas, of course. Hydrogen is certainly a gas. What about ammonia? You guys usually, you can smell it. Like, think of the ammonia bottle that you have like a cleaning agent or Windex. You smell it, right? Immediately, it like pops you in the face. So what state of matter is that? Definitely gas, because solids are not moving up towards your face. Liquids are not really. There's the gaseous component. So now all I want to do is write out the K. Let's do KC expression first, and then we'll do KP. Okay, so KC. Get me started. Done. So remember, it's always whatever what. Okay? Okay, I'm going to put concentration though, concentration of ammonia. So I'm not going to put the 2 inside of here, it's just that product raised to the 2nd power. Okay, Elizabeth, pick up. Because we've used our product, the only product we have. Okay. Okay, so concentration of N2 raised to the what power? Elizabeth, what's the coefficient from nitrogen?
1.
A 1, right? So I don't have to put the 1 there, nor do I have to put it here, but it's nice to at least recognize. Camilla? Raised to the power 3. Very good. That's it. So that's your setup for K, indicating products of reactants. So let's go to another table. Let's go ahead and write out the the pressure version of the same thing. Write out the pressure version of the same thing. All right, Ariane, go ahead. What would I put on top? I'm still using, stay with me, okay? So I'm still using this reaction. I'm just rewriting this in terms of pressures, not concentrations. NH, so pressure, right, partial pressure, NH3, okay, raised to the second power, because that's the coefficient of 2. CJ? Okay, Cole? Raised to the third power. Very good. Okay, so that's our general setup again. And now we're going to start to get to the point where we can try this a little bit more on our own. You guys do this one down here. And I prefer you to write it in KC. So KC for this one right here. This is aqueous. All right, Nana, what do you think? Get me started. For this reaction here, I want to know just the expression. So it's always, guys, let's go to this chant goes. It's always whatever what? Products or reactants. So we cannot put reactants on top ever. Okay, so start over for me. Well, what do we notice the state of matter this one is? Okay, who saw that one? Who saw solid? Half of you? Oh my gosh. Okay. So can I put the solid in this expression? No. But I don't want to not put anything there. So what can I put there instead? A 1, because that 1 is going to be like a placeholder. It won't affect our calculation at all. It's just kind of hanging there. All right, keep going, Nana. So we've handled the only product. Now. On what? On bottom. Okay, so what concentration of NH3? Jacob, pick up.
Then you have the concentration of H2.
Okay, that's it, because everything's to a 1 to a first power. Okay, just want to make sure you saw the solid so you're aware of what's going on. That's gas, that's aqueous, those are totally fine. Solids are no-go. All right, I want you guys to do 1, no. You guys do 2 right now. Go ahead and do 2. Just write the Kc expression, and then do 3 and 4. I'll scroll 4 up in just a second. 2, 3, and 4. You don't have to write down the VCE, but if you want to for your notes, that's yeah, the Kcs. Scroll up a little bit so you can see 4 a bit better. And you can see 5. And that 5 will be our last one for now. scooch back down here. And when I call your name, you just follow in line wherever we are in the chart, okay? So I'm going to tell you, we can write this expression as a KC, a KP. The really generic way of writing it is called KEQ. What do you think EQ stands for? Equilibrium. It's just a really generic way of writing it, but we will always use concentrations in that place. Okay? What do you think, Ariel? Get me started. Okay, so concentration of carbon dioxide raised to the first power, so I'm just not going to write it. Maverick? Okay. Raised to the what power? 1, right, Camille? Good. What did you skip here on purpose? The solid. Very good. Okay, so that's good for that one. Number 3, this one down here, I'm going to partition off. Mirror, KC or KQ, whatever you want to call it. What am I writing on top? For number 3.
Oh. See, wait, yes.
There's no C. It's always what, guys? Whatever what. Products or reactants. Mirror, give me the product.
H2.
Give me the whole product.
Oh, H2CO2.
Okay, so carbonic acid is the product. That's the numerator. Over what, Hannah? Concentration of CO2. Anything else? Good, because the liquid, pure liquid is out, so we excluded that one completely. Okay, number 4, Riley. Mg2 plus. Okay, that's the concentration of the Mg2 plus ion. Bailey? Br minus ion, say again. So raised to the second power. Okay, and Munir, do I put anything else here? Okay, so I'm actually gonna leave it like this. You don't have to put over 1 because we need the one on top. If there's a 1 on top, is like what else you're gonna put in the numerator. But this actually would be fine as is, and this is actually how I prefer it. You don't have to put over 1 unless you want to, but that solid is excluded from our process. All right, one more. Estes, get me started on 5. Okay. Okay, so no solids, so we're going to put water.
Oh, no, it's actually going to be 1 over.
Okay, why did we put 1 here?
Because it can be solid.
Good, so everybody sees pure solid, pure liquids out. Keep going.
What's the statement there?
That's a solid. So this is just 1. K is equal to 1 here because there is no equilibrium expression for this specific one. Very good, guys. Okay, so give me where you are on this 1 out of 10. Can you write an expression? Do you know what a K value stands for? This is no, not just 1 out of 10, so just seeing where you are. And do you know what a K greater than 1 and a K less than 1 refers to? All right, I'm feel good about that. We're doing all right. All right, so quick strike break. Send me somebody up here. If you start breaking, if you're going to get it in now. I'll say the extra guy. I'm guessing. I know I'm giving you way more than 4, but this is how we're rolling right now. If I didn't give you enough, I will give you enough more. Alright, so we're actually going to start on alright, make sure you get one right to me. If you have extras, yeah, that'd be great to bring up right on back. If you don't have enough, let me know, okay? Thanks. Alright, so this is your paper, okay? So I want you to start on number 2, and I just want to give you the tip that it says at equilibrium. It's telling you that this reaction is already at equilibrium, so you are good to go. You are going to plug numbers where they belong in the equilibrium expression. So it's having you write the equilibrium expression first for this reaction, and it says what's the value. Okay, see if you can do that. Let's see what you guys come up with in your table. Can you calculate it? You know that. It is teeny tiny writing, but that says H2 plus I2 equilibrates to 2HI. We're starting on number 2. Walk around with that. If you need a calculator, they're just going to walk around for like a minute. He's moving fast, so. Do compare with someone nearby, because you know those little goofy calculators in parentheses. All right, get ready. You're gonna help me get this set up, okay? So expression for A, done. Get me started. K is equal to concentration of HI raised to the second power. Andrew, pick up. Okay. All right. So everybody has this set up, right? Check. All right, because that's the easy part. You've done this 5 times, like in the last 5 minutes. So all it says now, and this is really important. I know you're still on your calculator. Hold on for a second, okay? You should have had a moment to calculate if you need to. When it says at equilibrium, and this is called the equilibrium constant, aka equilibrium expression, because the expression is this part over here. You are plugging stuff from the equilibrium values right on it, okay? So what am I plugging in here? 1.35 times 10 to the negative second molar squared. Don't forget the squared, right? Over, what's the H2? 4.56 times 10 to the negative third molar times 7.38 times 10 to negative third molar. Okay, and what did we get when we plugged in our calculator? Hopefully correctly. Give me any scientific notation. Actually lies, you don't need scientific notation. 5.42. Give me a thumbs up if you got that. Alright, and then scrunch your face if you put it in incorrectly, because you didn't put parentheses in the right places. Okay, so this is K, right? Talk about what K represents for this particular one right now at your table. What does it represent? Alright, Ryan's table, what do you guys say? What's K represent?
Equilibrium constant.
It does, but this K specifically is showing us what about equilibrium?
That's the rate of reaction.
No, right. That definition of equilibrium is rate forward equals rate reverse. This K value is 5. It's significant. So this K means greater than 1, which means what?
More product.
More products. Products are favored. Products are in greater quantity. The graph has products on top. There's a lot of ways to say that. Okay, so do you feel good about plugging numbers in?
Yes.
I mean, it's just plugging numbers in, right? And if you can't plug numbers in at this point, shame on you, but make sure you put your parentheses in the right place. There's one more set that we're going to do. It's on the right-hand side where it says calculations involving equilibrium constant examples. You guys see that one? Yeah? Okay. So let's go ahead and do number 1. Can you guys do that at your table groups? Actually, I mean, you can keep going. 1, 2, and 3 are the ones that we're going to do. 1, 2, and 3. Talk it out at your table. Get your expressions set up first. I guarantee that is the most helpful step. Set up your expressions first. Thumbs up if you're done with the first example. If you're done with the first example, go ahead and check your work on the board. PCl3 product times Cl2 product over PCl5 reactant. Plug, 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 low number. So give me a thumbs up if you got 0.04 or something. Okay, and everybody knows that K value is less than 1, reactants are favored. Keep moving. Just give me a chance to get some feedback as you go. Best part, everybody was fruits. Right. Do not neglect to set up the K expression. The K expression is the most important first step. Just plug in. That way you can support yourself when you go back and check your work. Right, give me a thumbs up if you're on number 3. Give me a thumbs up if you're on number 3. Give me, one second. Give me a thumbs up if you set up your K expression as the methanol concentration over carbon monoxide times hydrogen squared. And you plugged in each value you know, put an X in for the question that is asked of you, which is the hydrogen gas. So we're just plugging X in there for the sake of understanding that's we're solving for X. And set equal to the value of the equilibrium constant K. Alright, who's here? Shake your head or something, okay? Okay, we're here. Now it's just algebra, right? A 5th grader, hopefully, who took algebra 1? Okay. 8th grader? I don't know. Somebody can do this. Alright. How do I isolate X? Multiply by what? Okay, and X squared, because I can't leave this X squared in the bottom because it's going to stay in the bottom and I'm never going to be able to get it out. So if I multiply by 1.42 times X squared on this side, I'm also doing that over here. Okay, so this is gone out of the picture because this cancels over here, and I'm stuck with 0.818 is equal to, what's this times this? 2.25582. I mean, I don't want any rounding error, right? So So what I've done is I multiplied the point, or 1.609 times 1.402 times x squared. This and this are equal. Now how do I get x squared by itself? What? Divide by the 2.2 number. 582. Okay, so that cancels. So then what's 0.88 divided by 2.2550 or 82? What is this? Somebody. 3626. That looks good. Okay. Equals what? X squared. So I'm really close. How do I solve for x? Square root the whole shebang, and what do we get? Equals x, which equals the hydrogen concentration. Muy bien. So don't just depend on your calculator. Write out a couple steps so that you can follow through and you can check your work as needed, okay? All right, take about 30 more seconds or so if you're still processing that one. I'll leave that work up there. We're going to do one more, and this one more is a little bit more challenging because it has you recognize the whole process of equilibrium. Because I've been giving you simple equilibrium values, like I just gave you the end part, right? We didn't travel together the journey of the reaction. I just said this is the end. So we're going to change this up a little bit. I think everyone's on the same page with me. Can I go past this? Great response, guys. Got it. Okay. No, you guys already know that. You're good. Okay. This I thought I would just show you that the process of equilibrium is occurring in your body right now. Equilibrium is useful in every form of reaction in your body. There's a simple balance that occurs. And so, for example, do you guys know what your pH is supposed to be in your blood? It's a little higher than 7, actually. We're a little bit on the basic side of our blood pH, but we keep it that way by equilibrium reaction. Glucose, do you know what your glucose levels in your blood are supposed to be? It's like so many milligrams per deciliter. I think it's per deciliter. So I think it's about 100 milligrams per deciliter. But you keep it that way because your insulin's going to pump and make sure your cells take up glucose. If you have too much, you're hypoglycemic or hyperglycemic. If you have too little glucose, you're hypoglycemic. So we keep our body in check with equilibrium at all times. And then, of course, our carbon dioxide to oxygen levels, we keep that in check with equilibrium reactions. And then if you ever make rock candy, it's simply an equilibrium reaction. There's so many equilibrium reactions in the world. So I feel like that was important for you to know. Give me a thumbs up if you can do every bullet in purple. Give me a thumbs up if you can do every bullet in purple. Isn't one? All right, push on those thumbs up. All right, talk in your groups for a moment to explain what each of these means. Explain what each of them means. Go. Talk them out, put them in your own words.
It's like that graph, equal concentration.
All right, take 10 more seconds. All right, come back to me. We're going to do these next two in a couple minutes, okay? And that will be it for equilibrium. there's one more, like I said, there's one more part of the journey. So I've started you off at equilibrium. So we kind of skipped all the traveling. We just went to the end, right? So occasionally, you're going to have to construct something called an ice box. Write down what ice means. ICE means ice, ICE, it's right here in front of you, means what? Initial change and equilibrium. I try not to have secrets. It's always usually on the board if you just watch, okay? So we're going to do number 3 and maybe number 4, and this is on your paper on the left-hand side that we were working on initially. So watch me set up the first one, listen to the explanation, listen to what we're talking for, because it's a little different than before. All right, so write the equilibrium constant expression. Okay, well, we can do that, right? Okay, so A, equilibrium expression. K is equal to what? That says 2A gas plus 2B gas equilibrates to C gas plus 4D solid. Ready when you are. Concentration of C over, okay, because we're excluding D as a process because it's a solid. Over what? A to the second times B squared. Okay, we always write the expression first because if not, we forget to include like squares and cubes sometimes. Oh, okay, so it says the initial concentration. This is not equilibrium, okay? The initial concentration of A was 4 molar and B was 4 molar. What would the constant be? What's it asking for? It's asking for what? K. When it says the constant, it's asking for K. Be it at equilibrium, okay, so now we're given equilibrium values of A was 2 molar, or at equilibrium if 2 molar of A has reacted. So now we're seeing that we're given initial values, we're seeing some changes occurring, and then it's telling us to calculate equilibrium constant K. So what we want to write out is this reaction, kind of big so we can work with it, in a 3-row table, okay? So write 2A plus 2B equilibrates to C plus 4D. We may not need D, but we're going to write the whole reaction out just in case. Okay, so what were the letters that I told you we're going to set up? It's called a what box? Ice box. So write down the side ICE as in initial change in equilibrium. Equilibrium is kind of like our summation point, so I like to put a line here to indicate like everything below that line is the equilibrium stuff. Okay, what was the initial concentration of A? So we're going to put the 4.0 molar under A. What else was provided for us initially? So 4.0 molar B. So check, we've used both of those values. Okay, so think about what this reaction is, guys. It's in a test tube. We pour 4 molar of A in. We pour 4 molar B in. Before the reaction began, were there any products? No, plus it doesn't tell us that, right? So we're assuming we have 0 of both of those products because we were not told we had any, and it kind of makes sense. We're just starting with those reactants. No products are present yet. Okay, so it's reacting, right? Now, what would the constant be if at equilibrium 2 molar of A has reacted? What does that tell me in this box system? That's the total change of who? Of A. So 2 molar of A has totally reacted, right? So if I have 4 molar of A and 2 molar of A is reacted, well, how much is left? 2. So we're going to take that and subtract it, because change means to react. So we're going to subtract 2 molar of A, and that's going to leave us with what of A? 2 molar of A. 2 molar of A. So what's different here is that this change is the actual really important part. We have to recognize that this is a 2 to 2 to 1 to 4 ratio, right? So if 2 molar of A is changing, it's the same ratio with B, right? Because of the 2 to 2 ratio, how much of B should also change? 2 molar, because it's like the idea that's the same ratio, so it's reacting the same quantity at the same rate. So we are reacting 2 molar of B. So how much of B is left? 2 molar. Okay, now C is made in a what ratio? 1 to 2. So is it being produced or is it being reacted? Produced. So when I produce something, do I subtract it or do I add it? Add it. So I'm definitely going to add over here. But how much of it do you think I'm going to add? Say again?
4.
So I'm making 1 C for every 2 A's that react. So I'm reacting 2 moles of A, or 2 molar of A, but it's only going to make half of C. So it's making a 1-to-2 ratio, aka half. Okay, so this is only going to be added in a half ratio amount, 1-to-2 ratio. So this is a 1 molar addition. Now, I could have us write out the stoichiometry for every single step of this, but if you understand that you have a quantity, that's the only quantity provided to us in the whole problem, you use this golden number right here, and you use the ratio to basically fill out the rest of the chart. So if I cared about D, I don't, but if I cared about D, how much D would be produced? Say again? So tell me the process. We said 2 molar of A reacted, but D was produced in a
4-to-2 ratio, so 2-to-1.
right. So that's produced in a 4-to-2 ratio. If I have 2 molar reacting times 4, what's 2 times 4, guys? 8 divided by 2, 4. That's how much changed. So you literally use the ratio 4/2. So that would be 4 molar being produced. Okay, so then we fill out the bottom of this chart. And these now are the equilibrium numbers. Those are like, if I, instead of telling you the whole story, the background, the journey we took, I would just be like, hey guys, equilibrium values are 2, 2, 1, and 4. Find the equilibrium constant. How do I find it now? Just plug it in. Okay, so I'm plugging in what goes on top. Okay, so 1 molar over. Okay, so I used C already. Now I'm going to use A. 2 molar squared, because that's what we wrote for A up there, times 2 molar squared. All right, you can do this and you don't need a calculator. What's 2 squared?
4.
Okay, so what's 2 squared?
4.
What's 4 times 4?
16.
What's 1/16?
1/16.
Point. 125? 625? Okay. And obviously this K value is less than 1. Okay. I'm going to halt there for a moment on the icebox. We're going to multitask here, okay? Go grab laptops in case we have time to start tea. Okay, go grab laptops. And I'm going to introduce you to Le Chat's. Le Chatelier's principle. I can't do that way. I wish. Alright, and you're just getting logged on for me, and you're going to pay attention up here, okay? You're just getting logged on for me, and you're going to pay attention up here. Okay, so we went through equilibrium, and now we're going to go through what happens if you modify equilibrium. Oh no! Okay, so imagine this. You get enough sleep, you get enough to eat, you get your homework done in a relatively short amount of time. People are being nice. I'm saying imagine this, okay? Your life is in balance. Your life is like perfectly balanced between it's a little bit rigorous and challenging, but it's also like calm and chill. You get to watch Netflix, you get to play outside, you get to hang out with friends, you get to sleep, you get to have your personal time, you get to have your friend time. I know, perfect world. All right, shh. You are in balance, okay? All of a sudden, you have to study for an exam, and it's like the end of the world, and you have to just totally wipe out all your sleep. I've taken sleep away from you. You're in disbalance, right? You're in disequilibrium. Oh no. What can I do to get back to that stable state? What did I take away from you? Sleep. So what would I have to add back? Sleep. If you take away something, that pulls you out of equilibrium, you have to get that same thing back. So there's a way to do that, right? If I took away food from you, You'd have to find a way to get food back, right? That would be how you get back to equilibrium. So that's the whole idea behind Le Chat's principle. Write down Le Chat's principle, at least so you understand that it's called Le Chatelier's. He's a Frenchman, but we're going to just call him Le Chat. It's not chat, it's, yeah, Le Chat. So we're going to follow this map for a second, and then we're going to watch the video. You're just getting logged on the computer. Where I'm hoping I give you some time to get to pink, but I just want to get you there in case. So here we have, here's Le Chatelier's principle. That's the whole name, okay? So a system's at equilibrium. It will respond to stress. So like me taking sleep away from you is a stressor. It will respond to stress to reduce that stress. So it's going, you have to respond, okay? You have to find a way to respond. And I'll give you a tip. This system is a lot simpler than your life, okay? Your life, you can respond to stress in like 100 different ways. The only way that this equilibrium reaction can respond to stress, you guys with me? You guys with me? Okay, can you guys stop? Thank you. All right, so the only way that this system can respond to stress is to shift left or shift right. What that means to you now is actually in the form of a reaction. Which is the left side of the reaction? The reactants or the products? That means reactants, right? So put reactants right there. So that means shift towards reactants. And which side is the right side? The product. So put products right here. All right, hands off the computer. You're with me. Maybe halfway shut your computer if you don't have any willpower. Okay? All right, so the only two options this reaction has is wet and wet. Shift left or shift right. And what's the whole deal behind this? Why is it shifting left or shifting right? To do what? To make up for what it lost, or to make up what kind of stressor it experienced. Okay, so you're at the happy system, okay, and it's going to respond to the stress by trying to shift left or shift right. And this is like a Q versus K thing, but more than anything, we just want to know if it's going to shift left or shift right. That's it. So the whole principle behind Le Chatelier's principle, the whole idea behind Le Chatelier's principle is the reaction gets stressed, it responds by shifting left or shifting right. That's it, okay? So here are the changes or the stressors that could be had within a reaction. So you do need to write these down, and we will talk about each of these individually. Once you get done with what's on the board, I think this is about as simple of a definition I can make for Le Chatelier's principle in your own words, like something that makes sense. So I'd like for you to write something like that down if you need that for your own notes. Alright, so the whole idea behind this is that once we know equilibrium is achieved and we cause a stress or create a change, our job is to predict that the reaction is going to relieve that stress by either shifting left or shifting right. Sometimes there's something called no shift. It depends on what's happening. So these are the series of changes that could occur. So if in our system it's cold and we make it hot, well, it's got to shift a direction to include an incorporation of energy. So if we change the temperature, it's really, really helpful for us to know if the reaction is endothermic or exothermic, because then we can make a prediction, because generally what we think of is if you have A plus B yields C plus heat, for example, or kilojoules, would you guys call this a reaction that's endothermic or exothermic? Exothermic, right? Because the delta H is negative because the heat is a product. It's really just being produced as an excess form of energy. And if it was an endothermic, the reactant would have the energy incorporated. If you add or remove a reactant, the problem is, oh no, I remove a reactant. What do I need more of now? Reactants. Well, if I remove a reactant, which way should I have to shift to make those reactants? Okay, where are the reactants in the reaction? They're on the left side. If I remove them, my job is to get reactants back. So which way would I have to shift? To the left to make more of the thing I took away. If I remove a product, oh no, I don't have enough products, what do I need to do? Shift to the right to make more products. You're always righting your wrong, fixing your mistake, fixing the thing that was taken away or added. I'll get to the common ion effect shortly. With the pressure changes, this one's really important to think about in terms of number of moles of gas. Okay, that is the most important part to think about when you get here. And so you have to count moles of gas, meaning count the coefficients or add up the coefficients of the gaseous products and reactants. Question? It basically means to increase the rate of the reverse reaction or increase the rate of the forward reaction. So to make more product or make more reactants by making the reverse reaction happen more quickly, or make more products by making the forward reaction happen more quickly. That's what I mean by shift. Good, very good question. Okay, so let's look at a couple of examples here. Okay, so I'm going to walk through this whole example with you first, okay? So this is the formation of ammonia from its elements. Notice that it's at equilibrium. And what do you already know about this reaction when you see this? Okay, so we already know it's exothermic, so that's good for us to know, just to have on the side of our papers someplace. I don't know if I printed this one for you. I don't think I did. Go ahead and write down this reaction. Or if you have room where you wrote it before, you did write this reaction down. But we're going to talk about what's happening with, to the rates of forward versus reverse. So when I say shift, we're going to talk about what that means in reference to rates of forward or reverse reaction. All right, so listen to the story here, okay? It's at equilibrium. This is the perfect balance it can achieve. If we heat the vessel, the test tube or the flask or whatever it's happening in, if it helps you put flask there versus vessel, here's the problem. I have now incorporated more heat or energy than I should have. So I've increased energy. Well, where is energy? Is it a reactant or is it a product? It's a product, right? AKA, I've increased the products. I now have a problem. I have too many products. Well, how do I get rid of products? Do I want to go towards products or do I want to go towards reactants? Good, I want to go towards reactants, which is, in this case, a shift left. Okay, so the answer here is shift left. And what does that do for me? If I shift left, it consumes reactants or products. Okay, so if I go this way, if I go to the left, I'm using up which side of the reaction? I'm using this side up, right? I'm using up the products, and I'm forming what? Reactants. That's my job. Because my job was, oh no, got too many products. Yikes, how do I get rid of this increase in products? I need to consume this side. I need to use it all up, or some of it up, and then go the opposite direction. And in that process, I consume products and make or form reactants. That's what I'm doing every single time I shift left. In every scenario shift left, I always consume products and take away or make reactants. Okay, so now let's consider the next one. We increase pressure. Well, I don't see pressure anywhere here, so now I have to assess the situation. How many moles of, so gases are what's causing pressure, right? Gases are colliding with container wall. How many moles of gaseous reactants do I have? Loud and proud, people. 4. 1 plus 3 is 4 moles of gaseous reactants. How many moles of gaseous products do I have? Okay, so 2 plus nothing, right? So 2 moles of gaseous products. All right, so here's the problem. I've increased the pressure. What does that mean about collisions right now with container wall? There are just tons of them, right? Too many. So there right now, the problem or the stress are there's too many collisions with container wall. All right, so that's the problem. Who's going to fix that problem? 2 moles of gaseous products or 4 moles of gaseous products? Who's going to alleviate that? No, the problem is, I got way too many collisions. I need to fix it. Do I want more moles of gas in there colliding, or do I want less moles of gas in there colliding? I want less, because your job is to alleviate that stress, to fix the stress. So too many things colliding. How do I fix it? Shift to the right. I want to make less collisions happen now. So I'm going to shift right. And that's because there are what there? Less moles. Okay, so identify the stress and find a way to fix the stress. So the first one, stress was too many products. How do I get away from products? Go the other way. Second stress was I have an increase in pressure, which to me means too much stuff bouncing around. How do I get away from too much stuff? Go to the side with less stuff, less moles of gas. Okay? So now the problem is I've removed the ammonia. Okay? What did I really remove? A reactant or a product? Okay, so I took away a product. Oh no, I don't have enough products. How do I get more products? Shift which way? Shift to make more products. Shift right. So you identify the stress. Oh no, not enough products. Fix that stressor, fix the problem, go towards products and make more of them. That would be a shift right. Okay, what's the stress here? Okay, so I've artificially increased the reactants, which is where H2 is in the reaction. Okay, so I've added increased reactants. Oh no, too many reactants. How do I get rid of them? Make more what? I make products, which means a shift right. Okay, so as I notice I have too many reactants. I need to consume who? Reactants, good. And I need to produce good products. And in that case, consuming reactants and producing products is a shift right. Okay, it's like a logic game. You just have to figure out the stresses, figure out how you want to fix it. Decrease in volume. Got your box of air today? Okay, decrease your volume in your box of air. Carol, okay, what happened to pressure when you did that? An increase in pressure. Okay, that's our stress. Too much pressure, aka too many collisions. Okay, that's the problem, right? How do I fix it? Well, what is that? What is right? Okay, so decrease in volume caused an increase in pressure, which is too many collisions. So your job is to fix the too many collisions by shifting towards the side with less stuff. And that less stuff happens to be on the right side, because there were 2 moles of gas versus 4 moles of gas. But another way to think about the volume is, who fits better in a smaller volume? Smaller amounts of stuff, right? 2 moles versus 4 moles. Okay, that was a quick example. Look at the example on your paper. Let me see if you guys can do the first one together at your table. It's number 1 on the back side. All you're writing down is shift left, shift right, or no shift. Shift left, shift right, or no shift. talk it out, okay? Talk it out at your table. I want to hear you guys talking about this.
Shift left because say no shift because there's two moles on each side. I think so, at least because it's two moles in the shift right.
Go ahead and do the rest of them if you have time. I'm going to check this in about a minute. Oh, it's already 10:15. Find where that is in the reaction. Where is this in the reaction? So it's a what? Reaction or product? Okay, so which way do we want to shift it? Write it down. I'm just giving you extra chemicals. All right, come back to me. 3, 2, 1. Okay, so let's talk this out. Increasing temperature basically is saying I'm increasing what? Reactants or products? Products, because energy is kind of a form of temperature, right? Or temperature is a form of energy. So I've increased the products. How do I get rid of those? Shift left, shift the other way, right? Too many products, get away from them, go the opposite direction, right? Decrease volume, what does that do to pressure? Increases pressure. So I have to start doing what? Finding moles of gas, because solids and liquids don't do anything to pressure, right? So 1, 2, because there's 2 moles of gas over here, and over here, 2 moles of gas. Well, which side is favorable? Neither, so no shift. Okay, that way if there's not a favorable direction to go, you just say no shift because it's not actually going to impact equilibrium. Okay, HCl, I've added HCl, which is a what? I've added a what? Where's HCl, guys? Left or right? It's on the right, therefore it's a product. I've added a product. Okay, so that's the problem. I've added a product. Which way do I go? Left, because I want to go away from products. I have too many products right now. I need to go the opposite direction to consume them. Adding sodium chloride. Where's sodium chloride here? Nowhere. Okay, so sometimes we have something called the common ion effect, which I can go over tomorrow because I don't know if I have an example with that just yet. But because I don't have sodium chloride specifically here, here, or here, I have no impact on equilibrium, so I'm going to say no shift. Okay, remove chlorine, so I've decreased the what? Good, chlorine is a reactant. So, oh no, I don't have enough reactants. Shift left. I want to make more of those, right? I'm going to go towards it to make more of it. Okay, all right, so 1 through 4 is homework. You already did 1. Okay, and now I'm going to give you the option for the last, I'll turn announcements on in 7 minutes. For the last 10-ish minutes of class, either look at pink on your study guide or finish this up. Okay, you might be able to have time to do both. We'll check these tomorrow. Quickly, take the pass, okay?
Or no, you shift right. So
Bryce, you can get your computer from right here. You guys can look at pink on your own, but you'll notice there's some teaching moments and the rest of them are problems. The only one you can't do is...
Yes. Excuse me? I'm going to tell you that's that. Am I right on the board? I'm just going to go ahead and tell you guys this now, okay? There's one section on thermochem, it's 3B.
I don't give you a mass. I think it's this one. I don't give you a mass, so just omit that one. But you'll notice that it's gases. Okay, so gas laws. So that's a good review of your booklet, your gas law booklet. And then it gives you a couple like examples to work, like example samples, and then there's a couple questions embedded. They're not numbered per se all the way like the other ones are. And then there's a, what's this called? Heat curve, couple of examples there, and then thermochem. Okay, phase diagram's your last one.
So your pink is due tomorrow. Okay, so take some time for me off, that's what's in one. So this is. Because I kind of need to look what's actually.